Doing all right.
Mhm. Is everybody totally done with this semester?
A little bit.
Yeah.
All right. So I figured I'd just give a once over on I'd figure I'd pull up the exam on my side and give a once over to make sure that that you all have a good grasp of what's going to be on the exam. Then I wanted to take some extra any questions that you might have. All right, so let's see, do I actually have the final exam imported here? Let's see. Final exam, yes, I do. All right, so let's see. Oh, I see. All right, so it's not here. Let me go on to my my last semester's class, which has it. 2020 spring. Also, be sure to fill out your student feedback forms. We do actually read those and do take them into account. And they do have an effect when it comes to promotions and awards. So, which matters if you really liked your professor or your professor did a horrible job. All right, so final exam. So you're going to get some questions about here. Hey, here's a scenario for a data structure. Just like you had for the second exam. Here's a scenario for a data structure. Choose the data structure that best fits here. Make sense? So there should be about 3 questions like that. You'll have so as I previously mentioned this, but you will want to have a question. We'll be doing a question on quicksort. Now, quicksort, for some reason, this question really throws people. Mainly because they know the theory of quicksort, but not the practice of quicksort. So I think that's actually a good place to do some kind of review, because we all understand the theory of quicksort. Let's go ahead and share a whiteboard over here. So we've got this nice big whiteboard that we can, in theory, draw on. Okay, let's go ahead and just test it. Look, it's the way it's a smiley face. Doesn't that make you happy? No? I know it's so hard to please people these days. All right, quicksort. Let's go ahead, and the way I like to just to do these things is I will write the numbers 1 through 9 in a random position. Okay, and I'll just simply move around with them fairly well, not necessarily truly randomly, because there's a lot of going back and forth and alternating. So you got a lot more even on this side, but whatever. All right, suppose I tell you I want to quicksort this array. Okay. Now, now, mind you, I'm not going to say, hey, show me what happens after you perform quicksort out of this array, because after you perform quicksort, the answer is 1, 2, 3, 4, yada, 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 right? It's not what I'm looking for, right? What we care about is I want to see what happens on the first layer. So what we ask is, what is going to happen after you do the partition operation on it? I.e., what happens when we have selected our first pivot and descended up in the correct place, right? So here is the common answer that we get. Here's the common answer that I get that is wrong. If I were to give you this is the wrong answer that I get from a lot of students, which is 2, 4, 1, 3, 5, 8, 6, 7, and 9. Now, how did I get that? Well, So what do you do with your partition algorithm? Basically, you figure out what this guy is, right? You figure out your pivot item, which is always going to be the leftmost entry as our pivot. Okay, is everybody following so far? Right?
Yes.
Okay, so you select your leftmost entry as your pivot, right? So now, what are we going to do? Well, we select this guy, and then people are like, okay, let's go ahead and shift everything from the everything that's less than goes to the left, everything that's greater than goes to the right, and they just shift it over like this, right? So 8. So the small items are 2, 4, 1, and 3, so they go here, and the other bigger ones are 8, 6, 7, and 9. But that's not how the partition algorithm works. The partition algorithm does not work like that. It does not follow those steps because it's not you're not able to get it done in place if that's the case. The way the partition algorithm works is that you look up, is you start at the pivot, look up for the biggest you go up the array until you encounter an item that's bigger than the pivot. And once you find that, you start at the back and you go down looking for for an item that is smaller than the pivot. So let's go ahead and look up for an item that is bigger than the pivot. So, okay, we look up, we see 8 is the first item that's bigger. Now let's go down. Item that's smaller. So up and down haven't crossed. That is how we know we're going to be in an end condition, that everything's been partitioned, right? So what do? We swap those two. 5, 3, 2, 4, 1, 6, 8, 7, 9. Okay. So now we continue. Look up for the first item that's bigger. Look down for the first item that's smaller than the pivot. These guys have crossed. So that means that we are done with this. And what we do is that when we're in the end condition, we swap the pivot end down. So it becomes 1, 3, 2, 4, 5, 6, 7, 6, 8, 7, 9. Now, this is as opposed to what we had earlier, which was 2, 4, 1, 3, 8, 6, 7, 9. Right. Let's try this again with a bit more, with another example. Let's go ahead and put 4 as our pivot, and we'll do 1, 2, 3, 4.
Does it always use the first value
5.
as a pivot?
Yes, 6, 7, 8, 9. Okay, and that's a 1, not a 15, but I'm terrible at anything involving hands. Okay, so look up for the first item that's bigger, down for the first item that's smaller. Up for the first item that's bigger is this guy, down for the first item that's smaller than our pivot, right? Our pivot being 4. So up and down, so we'll swap them, and 1, 2, 3, 7, 8, 9, 1, 5, and 6. Now look up for the first item that's bigger, smaller, bigger, okay, and down for the first item that's smaller. They have not crossed yet, so we swap them 2, 3, 1, 8, 9, 7, 5, 6, okay, and now we look up for the first item that's bigger, down for the first item that's smaller, right, and they've crossed. Now here's why this works, but because we're going up and going down and swapping things, what's happening is that basically because we're taking the items that are bigger and swapping them over to the right side, and the items that are smaller and swapping them over to the left, what happens is that we partition it into basically, we partition it into these 3 pieces: the pivot, everything smaller than the pivot, everything greater than the pivot. And that's a lot easier to deal, and that's easy to change into the everything smaller, the pivot, and everything greater by taking the last item in the pivot, last item that is smaller, and swapping it with the pivot. In other words, taking down and swapping it. which is going to be 1, 2, 3, 4, 8, 9, 7, 5, 6. Make sense to everybody?
What happens to 4 at the end?
That is you return that as our pivot, and you say this is the index the pivot's at. So that's what we did. So now the pivot's over here in the middle, with everything smaller being left, everything greater than being the right. That makes sense?
So when they cross, we just switch the down with the pivot?
Yep. I went over this in the quicksort videos. You can refer back to them if you need to, but this is the way it works in the book. This is the way that it works in when you actually implement quicksort, because otherwise you can't really do it in place. Right? So this is how the partition algorithm actually works, and that's what makes quicksort actually, pretty quick at, sorting. All right. Stop share. All right. After that, we will also have expect at least one question on the theory of sorting. So like, hey, here's some algorithms. We have different algorithms and different use cases for algorithms. Why would you bother using this one? Okay. So you'll also have a hash table function, just like we went over earlier, which is, hey, here's a hash table. Here's a hash function. Let's go ahead and try to move things. And here's a hash function. Here's keys. Here's the strategy I want to use. Put the things into the right index. Let's go ahead and actually take a look at one of my a question from one of those other exams that I didn't get to do last time, but that was because of the time issues. I think this is a really good question. And if I didn't use it as a practice question, I would have totally used it. Maybe I'll do that next semester because it's a really nice question. All right. Okay, here we go. So everybody sees this guy. Stop share. Share, I want to be very specific about what I'm sharing. There we go. Okay, everybody sees this exam question. Should resize for everybody. Okay. Suppose you have some hash table. Okay, we've already got a hash table and we've inserted some elements. When you inspect it to see, you see that the result looks like the picture below. Being the good student, you realize this is a problem. What is the problem? Give an example of the hash function that could have arisen to this behavior, and what would be a better hash function. So this is the hash function. So first off, what strategy are they using? What strategy is being used here?
Quadratic probing, I think.
Not quadratic probing. Quadratic probing is a type of open addressing, which means look for the next available space. And the key feature of that is that each space only holds one item.
Also, I thought they were like being, so it's a bucket?
Bucket or chaining, that's correct. Either works for the term, bucket or chaining. I prefer the term chaining, so this is using chaining. So what is the problem we've got with this? We've got this hash table, what's the issue? Any takers? I know you're all burnt out and tired. It's fine, but
can I give a guess? I don't know. Like,
yeah, give a guess. I'm not gonna make fun.
Searching for the right element might take more time since there's a linked list on some entries. And
yeah, pretty much. I mean, you're in the right direction, which is that pretty much basically every index but 4 and 10 has multiple items in it. And there's a lot of empty spaces, right? Right? The average length, it should be evenly distributed in the linked list. It should be evenly distributed among the index, but it's not evenly distributed, right? So what is the hash function that might have caused this? So this is a bit of a puzzle. I like it because it's a bit of a puzzle. What caused this? Right? We've got index 0 at 0 and 30 at 0 and 21 at 2, 31 at 2, and 1 at 2. Okay? So what is the hash function that could have caused this behavior?
The number mod table plus 2? Maybe not.
Not quite. So
Is it just X mod 19?
X mod 19 would actually result in a much better hash function, right? Think about it. How would 30? Well, I mean, like 30 mod 19 would give us 11. So that already would be an improvement. I'm going to let you puzzle that out while I see what's up with my kid.
What's wrong? What do you want? You cannot make a rectangle out of sunglasses.
You would break it.
You can only make a triangle.
Hey, kiddo, I'm trying to work. I appreciate it if you would be quiet. It's okay. I understand that it's easy to get sad.
Why don't you try to find things that you can make into a rectangle? Is that a good idea?
He is sad because he cannot turn into a rectangle. So
Turn the sunglasses.
to turn sunglasses into a rectangle, which seems a bit difficult. And Patrick, that is correct. It is the last digit times 2. So if you notice, right, the zeros end up in index. Anything ending with a 0 ended up in index 0, and anything ending up in index with it ending with a 1 ended up in index 2. Anything ending with a 2 ended in a 4. 3's ended in 6. That is a hash function that could have, I suppose somebody could come up with something different, right? The person who wrote this was very mathematically oriented, and so they used that mathematical language. They said, give an example of a hash function, not the hash function. So yeah, but that is what I've latched onto. That this 38 ends with 8. 8 times 2 is 16, so it goes to index 16. A consequence of this is notice that every single odd index goes unused. So we literally cannot use half the table, right? Because any number times 2 becomes an even number. So, okay. So what would be a better hash function? As mentioned earlier, modding by the table size would be good. Or modding by 19 actually would be fantastic because 19 is a prime number, so we'd get some nice, good distribution there, right? But even just modding by 20 would probably end up being pretty good. So I think that's a pretty good analytical problem for hash tables. Okay, so let's go ahead and go back to my exam, assuming I didn't close it because I have been known to be stupid and, close things while I am still working on them, which I just did. Yes, but fortunately, it was saved by the reopen feature. All right, graph problems. So you'll be asked to do something depth first search or breadth first search, one of the two, right? And then the other, be sure to, we're going to give you a graph. It's not going to be a nice graph in the sense that it's not going to be drawn out for you. We're going to give you either an adjacency list or an adjacency matrix, and we're going to ask you to do breadth first search or depth first search on it. So your first step is you'll want to actually draw that graph. So then do breadth first search or depth first search as the question asks. And then there's going to be a question, and this happens every time we learn Dijkstra's algorithm. There's going to be questions on Dijkstra's algorithm. So why don't we go ahead and review Dijkstra's algorithm one more time, because Dijkstra's algorithm it's like free points. Like it's not worth 3 points, but it's free, as in gratis, because Dijkstra's algorithm it's a fairly straightforward algorithm once you get into the swing of it. It's a straightforward algorithm that is really, so let me go ahead and pull up a good one for you guys, because you guys deserve to see a good one. All right. So from this
Question on the searching the graphs, the depth first search and depth first search, will it be like
order,
choose the lowest number or whatever?
Order, but yeah, there will generally be a way. They will have a way to break ties.
Okay.
Mhm.
Thank you.
It will be like either it might be lowest weight, greatest weight, or alphabetical, depending on our preferences. We have different ways of mixing it up. So
sounds good. Thank you.
All right. So let's go ahead and open up this guy, share screen. We're going to share this guy. This guy's a good graph. I like this graph. It's fairly friendly looking. Okay. Let's go ahead, and we've got our now this person. Now the person who authored this test, he did do something that makes me go like this, which is that he named his vertices 1, 2, 3, 4, 5, 6, and that's terrible. That really, I want to emphasize, causes this, because I don't know about you, but it really confuses me, or it makes me work an extra mental step when I have to think, okay, wait a second. Remember, one is we're going from node 1 to 2 with a weight of 2, right? That extra, just making that extra mental weight of remembering that that you've got numbers that represent names and numbers that represent edges. So if you're ever in this position and you're ever a computer science professor writing test, or you're ever making examples, please name your A, B, C, D, E, use letters for the names. But unfortunately we have to do this. So all right, we want to use Dijkstra's algorithm to determine the shortest path for each from one vertex to another. Okay, shortest path vertex from vertex 1 to each of the other vertices. Update the entries in the table to the shortest known distance in a predecessor. So nice person already gave us the table. Awesome. So we want to update it, and we'll just run through the algorithm that says below the table, list the order they are added to the cloud of known vertices. Interesting way of putting it, but I suppose that was the metaphor they used for the class. Okay, so we start at index 0, right? So we start at 1. At vertex 1, it has a distance of 0 from vertex 1. And so now we explore the edges. So we go and we look and we ask ourselves, okay, which of these is the cheapest? Which of these has the shortest distance? Well, 1 has the smallest distance, so we're done with 1. So let's look at the edges that are coming out from node 1. 1 to 2 with a weight of 2, and 1 to 4 with a weight of 3. So 1 to 2 with a weight of 2 is 1 to 2 cheaper than infinity? Yes, that new path is cheaper than infinity. So we're going to replace it with 2, and we're going to say the new predecessor is 1. Make sense? Next, let's look at this other edge. Is 1 to 4. We have 1 to 4 with a cost of 3. Is that cheaper than infinity? Yes, it is. So 1 to 4 with a cost of 3. So now we've expanded our clouds, our known vertices. So 1 is done. Now let's look. So now we've got 2, infinity, 3, infinity, infinity, which is the smallest. 2 is. So now we look at 2's vertices, the outgoing edges from 2. We have 2 to 3. Sorry, 2 to 5. Right. This is why I say having names and being numbers kind of annoying. We can go from 2 to 5 for a cost of 3. But that we're not going to ask ourselves, is 3 less than infinity? What we're asking ourselves is the cost to get to 5 from 1 less than the cost we already know. So the cost to get to 5 is the cost it takes to get to 2 plus this additional edge. So it takes 2 to get to 2 plus the 3. So it costs 5 to get to 5. And that was less than infinity, of course. And to get to 5, so node 5, we're going to say, hey, you get to node 5 by using the 2 vertices. Next, to 2 to 3. So the cost to get to 2 is 2. The cost to get to 3 to 5 is, the cost to get to 3 is 5. 2 plus 5 is 7. Is 7 less than infinity? Last I checked, yes. So get there from 2. Okay. And so we're done with these guys. Now let's go ahead and see what is the smallest of the ones we haven't checked. 7, 3, 5, infinity. Which are the smallest? 3 is. All right. So 3, which is the smallest? You see again, why I hate using weights and why I hate using numbers for nodes. Which is the smallest? 4 is with a cost of 3. 2, 7, 3, 5, which is the cheapest. The cheapest distance is 3 for node 4. That's what we're going to do next. So let's look. We only have one outgoing edge, which is 1. It costs 3 weight to get to 4, plus 1 additional 1 to get to 3, to node 3. So it's 3 plus 1 less than what we already know. So the current cost is 7. So is 3 plus 1, 4 less than 7? Yes, it is. So now we're done with 4. So now we've got 4, 5, infinity. Which is smallest? 4 is, so that means node 3 is next. Node 3, it costs 4 to get to node 3, an additional 2 to get to 6 for cost of 6. Oh, and I forgot to update 3 to say, hey, we get to 3 from 4. Okay. We go to 6 from 3. And we see now that basically going from 3, that it costs 6 because we can go from this way, and this way. So we're done with 3. Now let's look at 5. 5 or 6, which is the cheapest cost? 5 does. It costs 5 to get to 5 plus 4. That's 9. That's not greater than the cost to get to 6, which is 6. So we ignore it. Done with 5. And then 6 doesn't go anywhere. So that is our Dijkstra's algorithm. Once you get to the end, it goes really quickly. Okay, so stop. So the order they are processed by the algorithm, and we could have kept track of that as we were going, but let's go ahead and use just the ability to have some memory. So clear. Right, I have to do this. Annotate, clear all drawings. Okay, the order we did stuff, well, we did 5 last, and we got to 6, and we got to 6 from 3 after we went from 4, which was 2. So there you go. That's the answer to that part. That was just a matter of remembering what I did, or actually keeping track of it while I did it. Okay, so.
So we got to 6 with a cost of 6, I think.
Yes.
So you followed the 3, 1, 2, but we got to 5 with a cost of 5. So shouldn't we process 5 before 6 since it has a lower value, a lower cost?
Oh, yes, yes, yes. We should have done 6 first.
6 should be
Oh,
last.
sorry, 5 first. Yeah, we did 5. Yeah, we did 5. Yeah, we did 6 last, not 5. My bad. Yeah, so the order was. Yeah, I see what you're saying. Yeah, so the order was 6, 5, and then we did 3. No, sorry, then we did 4, 3, 2, 2. The order they are processed by the algorithm. Processed.
I think
But
4 is before 3,
The
right?
question is, well, I mean, like we did. So like we visited, we finished 1, and then we finished out 2, then we finished out 4, then we finished out 4, then we finished out 3,
And 5, 6. Yeah, that's the
and
order I
5,
got.
then 6. Yeah, that's what we did. Okay. Now, let's see. We looked at some of these already. For that, but let's continue. I'm going to continue looking at my algorithm. Sorry, at my problem. So in total, you'll have about 8 theory questions. The next couple questions are relate to a tree, to trees. The next one is also trees / linked lists, and the next one after that is a hash map coding question. So that's what we've got going on. So you've got 3 questions. So you've got 3 coding questions, or 3 questions where you're required to write code. Okay. Any questions about any other questions about the final exam?
On the linked list problem, so we're not going to be required to do like all those, like we did on the first midterm where we had to like write methods from scratch for linked lists.
No. You don't necessarily need to. You can use the linked list data structure built into Java for that.
Okay, all right. So we can use all the methods.
Mm-hmm. Yes.
I messaged you about taking the test at a different time.
Mm-hmm.
Did
I miss it? Were you the person who said I had 4 finals in one day?
Yeah.
I think I told you. Didn't I could have sworn I responded.
You told me to choose a day, and then I told you one, and
oh, how embarrassing.
no, it's fine. I know
Yeah.
everyone's pretty busy.
Oh, hold on. I think. Oh, did you send it to me on Discord?
Yeah, it was just a Discord direct
Yeah.
message.
All right, so let's go ahead and. Okay. Oh yeah, you said the 14th was good. So yeah, what time?
How much time do we have to take the exam?
You have 2 hours to take the exam, plus you've got the late penalty. So
Okay, so maybe like 1 to 3, if that sounds good.
Sounds good. Does anybody else need to take the final on a different day? That would be next week, I believe. Yeah.
So Professor Rosen, so 10 minutes late is 1%, right?
Right.
Okay.
Does anyone else have any difficulties with scheduling for the final? No. All right. Any questions in general?
So are we gonna have to scan in files and submit them, or
You do not have to. The last there will be text boxes for your for your answers, but all your questions can be some. There will be a 0-point question at the end, where you can upload any work that you've done. So that if you have any leftover work, you can.
Do you have time for a demo after class, sir?
Yeah. I mean, I'm going to dismiss class soon since there isn't too much else to go over. And I figured that you all could use a break at this point. Is that it? All right. So otherwise, I will go. Otherwise, class is dismissed. I will go ahead and take demos.